folks. All right, well, today I want to get into a bit of a design concept. So the idea of abstract data types, or ADTs. So whenever we talk about abstraction in programming, we're thinking about expressing something from a conceptual viewpoint where we don't want to get bogged down with all the gory details of the specific data structure that we're going to use in the actual C++ syntax, and whether it's going to be an int or a long, or whether it's going to be a float or a double. So when we're talking about abstraction, we're thinking about things at a more high level, more conceptual point of view. Let's see, so for an abstract data type in particular, we were thinking about some way to describe a kind of information that we want to store, but at a conceptual level. So, we might think of, again, a student record as involving somebody's name and their student number and, I don't know, their GPA. So we're thinking of things at that abstract level. We're thinking about the concepts. We're not worried about whether the name is going to be stored as a string, or whether it's going to be stored as an array of characters, or whether we're storing it as multiple strings for the first name, family name, any other names. We're not worried about whether we're going to store the student number as an array of char, or as a string, or as an int, or as a long. Right? So we're just thinking about the ideas for the things we're trying to represent. So for an abstract data type, we're actually going to look at two things. We're going to think about the pieces of information that go into whatever we're thinking about. Again, the pieces of information that go into information about a student, or the pieces of information that go into inventory information about a product. So we think about the kinds of information that belong in one of these things. And we'll also think about the kinds of operations that we want to be able to perform on it. So if we're thinking about a student record, for instance, then we might decide, okay, well, I want to be able to get at any of the individual fields. So I want to be able to look at the name, or look at the student number. I want to be able to maybe check the validity of the student number. I might want to be able to look at the GPA or set the GPA. So you think about the kinds of operations that you want to be able to perform. Now, if I was thinking about my abstract data type as being an entire class's information, like the information for all of the students in a course, then my information might include a collection of all of the students' records. So, again, I'm not worried about whether it's going to be as an array or as a linked list or anything like that. I'm just thinking, okay, well, there's going to be a bunch of student records that I'm keeping track of. Some of the operations that I'm thinking of for that collection might be things like, well, I want to be able to go through the list of student records and find a student by name. Maybe I want to be able to print the student's information sorted by marks, or sorted by student number, or sorted by name. I want to be able to insert a new student record. I want to be able to update a student's GPA, or I want to be able, maybe I've got information on the marks for each individual assignment for a student. Maybe I want to be able to go through and update a student's mark for a particular assignment. So I'm thinking about the kinds of operations I want to be able to perform, and the kinds of data I want to store. But again, from an abstract point of view, not worried at this point about whether they're arrays or lists or strings or character arrays or whatever it might be. So, abstract data types, the information we're worried about, and the operations we want to be able to perform on it. So again, my student record ID. I might have the name, the student number, maybe the fees that they owe. What kind of operations? Well, I want to be able to get or set the student number, or the name, or the fees. I want to be able to print the information. So what this sort of abstraction idea allows us to do in design is to start planning out our overall design of a solution for a particular problem. So start designing our software, but thinking about it at a conceptual level, and taking the view that I'm going to worry about the specific nitty-gritty code details later. I want to get a good, clean, logical design, a design that makes sense, a design that's easy to work with, and then I'll worry about taking the individual pieces and turning them into code, actually doing the implementation. So we might not even know what language we're going to be working with at this point. We're just thinking about, well, what kinds of things do I have to keep track of in this program, and what kinds of operations do I need to be able to do on them? So we're focusing on a very conceptual level when we're going through and doing this. And it helps us to simplify the design process, where we go through and think about things at high levels, come up with a good logical overall solution, and then bit by bit start turning those pieces into code, start implementing the solution itself. So the ADT, the abstract data and operations, and then at the implementation level, after we've figured out what kind of information we want and what kind of operations we want, then we'll start looking at what specific data types I want to use for each of the different pieces of information, whether I'm using a struct or an array or whatever it might be. And we can start looking at the code that we'll start using for the operations. So what kind of a collection of functions, for instance, am I going to use to support these operations on the actual data types that we finally settled on? Now, there's always going to be a lot of different designs that we can take for any different problem we're trying to solve. And there's always going to be a lot of different implementations we can use for any given design. So one of the things that we want to do is, once we've settled on our design, we want to stop and look at different ideas, different ways that we could implement that, and think about the pros and cons for each. Not just kind of blindly implement it the first way we happen to think of, but stop and think about, well, what are the different ways I could turn this into code, and what are the advantages and disadvantages of each? So, for example, if I've got some kind of a list of numbers, I've got a whole bunch of numbers I want to store. I have no idea how many there's going to be, and I want to be able to add new numbers to this collection one at a time. And I want to be able to keep track of the order of these things. So the first number I entered, I should be able to find as the first one. I should be able to keep track of the one that was after that, and the one after that, and the one after that. So there's got to be some kind of an ordering to this information. And I've got to be able to add new things to it as time goes on. I want to be able to search the list from the beginning to the end to find a specific value. And I want to be able to print the list from beginning to end. I'd also like to be able to go through and remove any one item from the list and keep everything else kind of in sequence. So these are the operations that I want to work with. This is the kind of data that I want to work with. What are my implementation choices? How could I turn this into code? What kind of data structures would I use, and what kind of functions would I use? So, first idea that springs to mind, maybe I'm just going to go with, I've got a bunch of numbers, I want to be able to get at them sort of in sequence. Maybe I just go with an array, right? I create an array, use a counter to keep track of how many things there are in the array right now, and every time I add a new one, I add it at the end of whatever I've added so far. So if there's 3 things in there, the next one's going to go in position 3, right? And if the one after that, it's going to go in position 4. So I keep track of where the next one will go and how many things I've got so far. Now, arrays, dead easy. We can do this easily. It's easy to find that last position, right? I've just got a counter that tells me how many things I've got in there, and I know where the next one is. It's fast to look up any position in the array. They're all in sequence. So, again, simple coding, nice and straightforward. The downsides, well, when I declare my array, or when I create my array, I've got to have a size in mind, right? When I actually create an array, whether it's by declaring an array with a fixed size or whether it's by dynamically allocating it as the program runs, I still have to have some fixed size when I create the array. And if the user is allowed to keep adding more things as time goes on, I never know if this array is going to be big enough, right? It might be too small. No matter how big I pick, it might be too small. And if I do go with something really big, just to kind of cover my base most of the time, then most of the time I'm probably wasting a lot of space. If the user runs the program a lot of times with small arrays and I'm creating these giant ones, or with small numbers with few numbers to store, then most of the time I'm wasting most of this memory space that I'm creating. So there are some downsides to the array in this kind of fixed size idea. And another thing that might crop up is, well, if I've got all the numbers stored in a row in my array, and I want to be able to remove one in the middle, well, you can't chop something out of an array. I'd have to do something like say, okay, well, if I'm removing the third item, then from the fourth item down, I'll shuffle them all over one position so they're all still in the right order. But that means that, if I've got 1,000 numbers stored or 10,000 numbers, and they remove the third one or the fifth one or the 10th one, then I'm shuffling like 10,000 items every time they remove something. So the remove could be kind of slow and clunky if I take this approach. But it's a possibility. So this kind of depends on, can I make a good prediction about how much space they're going to need, how big an array I'm going to need, and can I make a prediction about how often they're going to be removing things? If they don't remove very often, then I might decide that, okay, well, I'll just live with the slow shuffling when they remove. But it's definitely a possibility. So we think of that as our one idea for an implementation. And then we look at it, okay, well, second idea, what else could I do? I could take the linked list approach, where every time they add a new item, I insert it at the back of the list. Right? So we'll create maybe some kind of a struct where the number is in it, and then a pointer to the next thing in line. Or maybe a pointer to the thing in front of it and the thing behind it in line, so we can go either way through the list. When I want to insert, I just create a new item and insert it at the back of the list. When I want to print, I just go through from the front to the back, printing everything as we go. If I want to search, I go from the front and the back, looking for the items as we go, and stopping when I hit the null, stopping when I hit the back item. Removing, I search for the item, and then once I find it, I say, okay, well, what I'm going to do is make the pointers to the things before and after it kind of bypass the current item to chop it out. So for the item before me, I'll make its next pointer point to the thing after me. And for the item that's after me, I'll make its previous pointer point to the thing before me. So we can kind of chop it out of the list, and then we can delete it. So the operations become a little bit more practical, and we don't need to worry about how big this is going to grow. And as long as we haven't completely run out of memory, I can always add just one more thing. So initially, it's going to take up almost no space, right? So with our array approach, if we had to allocate a big array, then right from the beginning, it's taking up a lot of space. This one, we only introduce new space as we need new items. And again, we don't have to worry about picking a size up front. The downside is it is more complicated to write our functions to go through and manipulate linked lists, right? We've got our pointers to worry about, our allocation and deallocation to worry about, and we've got these kind of chains of pointers to think about. So the complexity might be the coding itself might be a little bit more complex. We've also got this idea that with the array, my array just had the numbers in it. So there wasn't anything extra other than the space in the array that I wasn't using. With my linked list, for every number, I've also got a pointer to the thing next in line, and maybe a pointer to the thing before it in line. So I've got, for each number, I've got the number and these two pointers. So I've got extra overhead to worry about. So I am taking up extra storage space in that sense. And the other thing is, with an array, this wasn't something that I asked for, but I knew that I could, if I ever wanted to, jump directly to any position in the array if I knew what position I wanted to go to. With a linked list, the only way you can get at things in the middle is by starting at one of the ends and sort of walking through the list until you find the one you're looking for. So access to things inside might be a little bit slower. But again, from the routines that they actually asked for, that doesn't appear to be a concern. It doesn't appear that we're ever actually doing that. So we do have, again, pros and cons for each approach, and we're going to try and decide for our circumstances which one makes the most sense. So we're going to look at it and we're going to think about, well, how much time do I have to develop a solution? Right? The array version might be quicker to do, easier to do. What kind of variation are we going to get in how many numbers they store? If they always store between 50 and 100 numbers, the array might make perfect sense. If they always store between 1,000 and 2,000, again, an array might make perfect sense, right? We allocate 2,000, and most of the time that's going to be just fine. If there's a lot of variability, then it might make more sense to go with the linked list approach. Again, how frequently we need to access something in the middle somewhere might be an influence, but how often we perform removes, especially from earlier, the middle of the sequence, is going to have a big impact on that array approach. Again, we said that if we've got big arrays and we're doing lots of removes, then we're frequently doing these shuffles of a whole bunch of elements down the array. That could get time consuming, and that could be a big strike against our array approach. So we look at how likely these things are and the impact they have on our two different implementation choices, and we pick one choice or the other. But again, we're taking the time to think about the choices that we have and the implications of our choice, and making an implementation decision based on the consequences that it's going to have. Right? So we're thinking about our design, thinking about the implications, and working from there. And those are some of the kinds of things that I want you to start thinking about when you're designing a program, when you're designing a solution. Think about what the implications of your choices are going to be, and don't just go with the first implementation approach that comes to mind. Right? See if you can come up with a couple of options and think about which one might be more appropriate under the circumstances. All right, I will leave that there for now.